Hi, so it's a great privilege to be here talking to you today a little bit about what I research, which is the field of cosmology. And in particular, today, I'd like to tell you about what happened in the universe before it got hot, before what we call the hot Big Bang model of the universe. So today, the universe is expanding. And that means that everything in the universe, all the galaxies, the clusters of galaxies, the dark matter around and inside those galaxies and clusters of galaxies, the radiation in the universe, everything is getting further and further away from everything else. It's getting more dilute with time. And if we wind the clock back, that means in the past, everything was closer together, everything was hotter, everything was denser. And as this happens, the universe at earlier times behaves in different ways. So today, there are galaxies and clusters of galaxies, but far enough into the past, there weren't any galaxies at all. They hadn't formed yet. And at even earlier times, even atoms or even neutral atoms hadn't formed, so we had nuclei of atoms and electrons flying around independently of one another at very high temperatures. Even before that, the nuclei of atoms themselves hadn't formed, so we didn't have the light elements, hydrogen and helium, but just the constituents, protons and neutrons and so on, again, flying around. And if we keep extrapolating this behavior back and back, then it turns out that at a finite time in the past, the laws of physics themselves break down and everything is on top of everything else. And we call that time a singularity. We don't really think it happens. We think something else will happen first in the sense of a new theory to replace the theory that is breaking down. So instead of a classical theory of gravity, maybe a quantum theory of gravity. But in this model, in this hot Big Bang model, we, in a finite time in our past, reach this point, this singularity. Now, the thing is that we only actually have direct evidence of this model, of this hot Big Bang model, back to about 1 second. That's when the light elements formed. And we know from the ratio of different elements of hydrogen, helium, and so on, that this model, this hot Big Bang model, is good back to that time. But before that time, we today think that something else happened. We don't think that this hot Big Bang model continued indefinitely. It probably happened to earlier times than about 1 second, after this thing we call the singularity, but at earlier times, a different kind of behavior occurred. And that's what I'd like to talk about today, what happened in this very early time, if we measure time from this sort of fictional point, the singularity, this time that was less than when the universe was less than a second old. So this is what I'm going to be focusing on. And our main theory for what happened at this time is something called inflation, or cosmological inflation. And I don't want to give the impression that this is a new thing. This theory is very old now. So when I was a graduate student, I went to a conference called Inflation Plus 25. So it was when inflation had been sort of around for 25 years. That's now about 20 years ago. So it's a very mature and established theory. But it's not proven in the sense of some of the other, the rest of the evolution of the universe, the hot Big Bang. So it is still open to some people questioning whether it happened, and we still don't have direct evidence for it, although there is a lot of evidence that something very similar to that happened. And today, as well as telling you about what inflation is and how it works, I would like to give a sense of that and talk a little bit about what perhaps some of the shortcomings of inflation are and what else might have happened. What are the other ideas, the alternative ideas for what happened at this very early time in the universe's history? So perhaps there was a bounce, perhaps before this expanding phase we're in today, there was a contracting phase before, and it bounced into our hot Big Bang model today. Or perhaps even there was many bounces, so cycles, and the universe went in cycles. These are other ideas, much less established than this theory of called inflation, but nevertheless, ideas that are out there, and I'll try and give you a flavor of that today as well. So this is the plan of the talk. First of all, to set the scene, before I can tell you about inflation, I need to tell you about the hot Big Bang, our standard picture of how the universe evolved. And so I'll spend probably nearly half the talk doing that. I'm going to talk about the properties of our universe that we observe today and this hot Big Bang model. And then I'll try and convince you of a need for something like cosmological inflation, something before, some kind of different behavior before the hot Big Bang. And essentially this comes down to the fact that the universe we live in is really special. It's set up in a really special way, and we would like to know why it is that way. And inflation explains that. So I'll move on to talking about cosmic inflation itself. And then I'll put inflation on trial. So let's see how well it's done, what its drawbacks are, and what the alternatives are. And actually, if you Google inflation on trial, you'll find a fascinating video of lots of experts in the field discussing this, whether inflation is the right answer to what happened in that time before the hot Big Bang, or whether something else, some alternative, was the right answer. So I urge you to do that after the talk. So let's start by talking about the size of the universe and what's in it, and how everything in it is structured. Because inflation, after all, is supposed to explain this. So let's try and set the scene. So when you have a chance, on a dark night, I urge you to go outside and look up and see all the stars in the sky. Because it turns out that, every dot of light that you see is a star, more or less a star inside our galaxy. And there are hundreds of billions of stars in our galaxy alone. So that brings me on to my first sort of demonstration of that. If each of these grains of sand was a star, then this bucket, which I'm going to pour out, would actually still only be a fraction of our galaxy. So there's probably somewhere in the region of 100 million grains of sand in that bucket. But there are 100 billion stars in the galaxy at least. So you need 100 buckets to illustrate the scale. And then beyond that, these stars and this group of stars that make up our galaxy is only one of at least this is a galaxy, not ours. It's the Andromeda galaxy. But this is there are at least 100 billion stars, or more, around 400 billion stars in our observable universe. So this image you're seeing at the moment is taken by the JWST telescope, so it's looking at just a tiny patch of sky, much less than a fraction of the full moon on the sky. So a fraction of it's about an arc second across. And in this image, there are thousands of galaxies. But if we look in a much broader range outside of this tiny image, and we try and survey all of the galaxies around us, then we'll see something like this. So this is from an experiment called the DESI experiment, which is mapping all of the galaxies around us in the universe. We sit at the center here, and we look out, and we see, in this survey, tens of millions, but we extrapolate that upwards to the entire observable universe, and we know there are hundreds of billions of galaxies in our observable universe. And another thing that I'd like you to take from this, and also from our sand here, is how these galaxies are arranged. So these galaxies are arranged evenly, in the sense that if I went to one region of the universe and asked how many galaxies there are, and then I went to another region and asked how many galaxies there are over there, there are roughly the same number in every place. So as we look out at the universe around us, it looks the same in every direction, and if we were able to go over here, it would look the same to someone living there, on average, as it does to us living here. Or if we were able to go over there, it would look the same again. So this property has a name. We call it homogeneity of the universe. And it's, again, going to be something that's central when I talk about inflation, because inflation is going to try and explain this property of homogeneity and isotropy, in fact, which is that the universe looks the same in every direction in the universe. Now, the other thing is that as we're looking out at the universe, the light that we're seeing has taken some time to get to us. So if we look further and further away, we're actually seeing the universe at earlier and earlier times. So the next image that I'm going to show is when we look at the universe, at light in the universe that's come to us from when the universe was about 400,000 years old, so very young. This is called the cosmic microwave background radiation, and this is the time when this image was taken, if you like, or when the light is coming to us from, when electrons and the protons were flying around independently of one another, when neutral atoms hadn't yet formed. And before this time, because they're flying around in this way, the universe is opaque. Light can't get through it. So when we look at the universe, this is the furthest we can see in light. And so it's a picture of the universe when it was very young. And it may look a little bit uneven. We've got hot spots and cold spots on it. But actually, the over and under densities that make the temperature a little bit hotter or a little bit cooler at this time are only at 1 part in 100,000. So they're really very small. The universe is even smoother at that time than it is today. Today, I said that the universe is very even on the larger scales. If we went over here, it looks very similar to if we go over here. And we see that even more clearly at a time before galaxies have formed, when we're looking back at the universe when it was very young. So let's put all of this together. And I can't resist showing you some of this video that, again, you can get on YouTube if you're interested in watching it afterwards, which is of the non-universe. So everything you see in this video is something that has been documented by humans, so something that has been mapped out by humans. And it's put together by the American Museum of Natural History, and it's really a beautiful demonstration of the properties that I've just been describing, both the size of the universe, the sheer scale of it, how many things are in it, and also the fact that things are arranged in this way, this homogeneity, this smoothness of the universe on very large scales. So it starts close to the Earth, it zooms out. It goes quite slowly at the start, but it'll get a bit quicker in a second. And the first thing you're going to see, of course, is things that are around the Earth, so artificial satellites that were put up into orbit. So we're not at cosmological scales yet. We're still very close to home. So we see these satellites. And then in a second or two more, as we zoom out a little bit further, you're going to see the orbit of the Moon, which is our own natural satellite, of course, around the Earth. And then as we zoom out even further, you see the sun in the background, and you'll see the other planets that are going around the sun. And it tells you how far we are away in light, seconds or minutes, which is the distance light has traveled in a certain time period. So we're still in the solar system, still extremely close to home right now. Then we're going to zoom out a little bit further until the solar system fades into the background. And so our star, our sun, is just one of these hundreds of billions of stars around us that make up this huge galaxy that we live in. And so in a second or two, we'll start to see the galaxy, the scale of the galaxy. So this is a really cool sphere here. This is how far radio waves from the Earth have reached since we started giving out radio waves. So now we see the Milky Way galaxy, and we zoom out even further. We see our nearby galaxies. And this video is a little bit out of date, so we've actually mapped many more galaxies even than are seen in this movie, but you see this image that's similar to the one I showed you before, what galaxy surveys have mapped out, these dots of light. Our best galaxy surveys at the moment have mapped out tens of millions of galaxies, and the next generation of galaxy surveys are going to go into the billions. And then eventually, as we get further away, we're also looking further back in time, and so we see the cosmic microwave background, light coming to us from an earlier universe from every direction in space, and we see the smoothness property of it. So the universe at early times was even smoother than it is today. And then it goes back in. So you can look it up and have a look. So now I've tried to tell you a little bit about the scale of the universe. I'd like to tell you a little bit more. Well, I've told you a little bit already about how it's structured. And I'd like to tell you about how it behaves with time and another property of it called its geometry. So it turns out the structure and the dynamics of the universe are really intimately linked. So how the universe is structured and how it changes with time go hand in hand. So let me introduce a couple of characters to tell you about this. So the first probably people know very well, which is Edwin Hubble. And he discovered this law, which is that when we look away from us in the universe, when we look sufficiently far away, when this property of homogeneity starts to be a good property, when we're looking at distant galaxies, that the speed at which a galaxy is receding from us is roughly proportional, or very close to proportional, to how far away it is from us. So galaxies that are twice as far away are moving twice as fast. And we're going to see in a second that this property is actually a result of the fact that the universe is smooth, is even, has this structure where it's the same everywhere. This law is sort of a result of that fact. But before we do that, you might wonder how he knew. So how did he determine this law? So the first thing, of course, he needed to know is how fast a galaxy was moving away. And, in my second small demonstration, I can show you how he knew that. So maybe you could put the sound on. And if I swing this around my head, hopefully you can hear that as I'm swinging it, the tone is changing. As it's coming towards you, you hear a higher sound than when it's going away. So I can stop that now. And the same thing happens to light. So the reason why this happens is that as the sound waves are coming towards you, they get compacted. And as the thing is moving away, the sound waves get stretched. So the frequency of sound is changing depending on whether this is moving towards you or moving away. And the same thing, as I was saying, happens with light waves. They also get squished up if something is coming towards you and get stretched out if they're going away. And so by looking at spectral lines, so lines of light in distant galaxies that we know what frequency they have if you're sitting right beside them and looking at the light. By looking at those the spectral lines in distant galaxies, what Hubble saw is that they're always receding. The light is always getting stretched. It's always what's called redshifted away from us. And the amount of this redshift is proportional to the distance. So the further things are away, the faster they're moving. The other thing, of course, he needed to know to determine this is how far away things are. And to do that, he used something called Leavitt's law, which is the other person in the picture, which is Henrietta Swan Leavitt. So she realized that there was a relationship in some stars that pulsate in terms of their brightness, a relationship between their pulsation and how bright they are. And if you know how bright they are if they were sitting beside you, if the star was sitting beside you, and you measure how bright it is when it's at a large distance from you, you can actually work out how far away from us it is. So this work was really central to all of these studies at the time in the 1920s and 1930s of the universe. Actually, it turns out it's much harder to know how far something is away than to know how fast it's moving. The Doppler effect or the redshift effect works really well for velocity, but it's actually quite hard. And still people are working on this thing called the distance ladder to work out how far things are away from us. And I told you that this law, Hubble's law, is a result of the property of the universe that it's smooth, that it's the same everywhere, on average in every position. So I have a little illustration of this now. It's just a sketch, so don't take it too seriously. But this is my universe, okay? And every dot here should be thought of as a galaxy or a cluster of galaxies. And you can see that if I move into one little corner of this image, it looks basically the same as if I move into another corner. And you've got to imagine that this image doesn't just exist on the screen behind you, but goes on in every direction. So infinitely far in this direction, infinitely far in that direction, infinitely far into the audience, and infinitely far away. So it's an infinite set of, or near infinite, it may as well be infinite because it's so big, set of galaxies with this property that on average every region is equivalent to every other region. And I could live anywhere in this image, okay? I could live all the way over there, I could live all the way over there, and I would see the same thing around me on average. But for convenience, I'm going to think about living in the middle of the image. So we said before that the universe is expanding, so those arrows were just to try and illustrate that it's going on forever in every direction. So let's say I live here in the middle of the image. And I observe some galaxy or cluster of galaxies at some distance away. Let's say I happen to know what distance that is. It's L away from me. And then I observe another one, this red one, that is twice as far away. And now we know that the universe is expanding. So what we're going to do, and we know that it's evenly distributed, so what we're going to do is just stretch this image so that all the positions of all of these galaxies and clusters of galaxies relative to one another stay the same, but we're stretching it out so the image gets bigger. Now, of course, that means it's going to move out of the screen, so the edges of the image are going to disappear, but the galaxies that you can still see maintain their relative position compared to one another. They're just getting all of them on average further and further away from every other. So that's what we're seeing here. I'm stretching the image. And I stretch it a bit more. And a bit more. And this is what we think is going on, or what we know is going on in our universe. The universe's expansion is like the space in between things getting bigger and bigger. So on average, the relative position of everything stays the same, but the space between it is getting stretched. So it's like this image is getting stretched. And again, remember, this image is going on all the way in this direction, all the way in, all the way out. Everything's getting further and further away. And a result of that is if I waited for some time until the star that or the galaxy rather, that I have in yellow here is twice as far away from where it started. So it was d away to start with, and now it's 2d away. Then the one that was 2d away to start with is now 4d away. So it's twice as far away again, but it's moved a distance 2d from where it started. And so this red one, it looks like to us, living at the blue dot, is moving twice as fast because it's had to move twice the distance when everything is stretched. So this law, Hubble's law, is actually a consequence of the fact that the universe is growing, but as it's growing, it's maintaining this property that on average, it's the same everywhere. It actually couldn't be any other way if this property of homogeneity and isotropy, this property that the universe is the same on average everywhere, is maintained. Then Hubble's law is the natural consequence. It really couldn't have come out in any other way. And indeed, this is one piece of evidence for this homogeneity and isotropy, the universe being the same everywhere, in addition to these direct measurements through galaxy surveys and of the cosmic microwave background. So the final thing I'd like to say a little bit about, just really briefly, is general relativity. So general relativity is our best theory of how gravity works. And within it, the universe or space-time is not a fixed thing, but a dynamical thing that has its own intrinsic properties. So space isn't just fixed, but is something that's dynamical and has geometric properties. And if we want a universe which is homogeneous and isotropic, which is on average the same everywhere, it turns out there's actually only 3 geometries that the universe could have. It could be flat, so that's the middle one on this image, which basically all that means is that when I measure the angles in a triangle, they'll add up to what I expect, which is 180 degrees. Or it could be open, which means that the angles will add up to more than 180 degrees, or it could be positively curved or closed, which is the bottom option here, which means they would add up to less. And again, this is going to be important as we go to talk about inflation, because it turns out we live in the flat option, that our universe is on average very flat, as well as everything being distributed very evenly. And we want to know why that is the case. So just to say, really, this is a 2D analogy. So you have to imagine yourself like an ant or something that's squished down to 2 dimensions and lives in this surface. So it can only explore the geometry by moving around or by making observations around it. And our real universe is, of course, a 3D, or the spatial dimensions, or at least a 3D analogy of these 2D geometries. But by making observations, we can actually tell which geometry we live in. So I said the universe turns out to be flat. And if it wasn't, things like the cosmic microwave background would actually look different to the way they do today. So you can see the middle picture here is a particular pattern of hot and cool spots in the cosmic microwave background. And if we lived in an open universe, they would be smaller spots. If we lived in a closed or positively curved universe, they would be bigger spots. So we can tell. And just for fun, really, maybe I can try and put all of those things together and illustrate what our universe looks like with this demonstration here. So, a few things to remember. Things are evenly spread in the universe on average. They're getting further and further away from one another. And really, you should be thinking about that as the space in between the objects expanding, space-time itself getting bigger, or the space itself getting bigger. And there's really no better demonstration of that than a balloon. Again, this is a 2-dimensional analogy. You've got to imagine yourself living in the surface of this balloon. There's no physical meaning to the depth of the balloon. You've got to think of yourself as a being that's 2-dimensional and inside the surface. But this is a 2-dimensional analogy to what we find ourselves in our universe. Everything's evenly spread, everything's getting bigger, and it's the space between things that is expanding. So let's have a look at what that looks like. So the universe starts small, everything's close together, it blows up. And as it blows up, everything, all the galaxies, the cluster of galaxies, everything in between, gets further and further away from everything else. And it's, like I say, it's the space-time itself is a dynamical thing in general relativity. So it's really the space between things that's expanding. It's a dynamical living thing, if you like, the space-time itself. Now, I have to be a bit careful here because I've literally got the entire universe in my hands. But I'm going to now slowly let the air out, and you can see these things shrinking back towards one another. And that's what's happening in our past. So as we go back in time in the universe, things get closer and closer together, hotter, denser, until there were no galaxies at all. And then at earlier times, not even neutral atoms, and at earlier times, not even the nuclei of atoms, towards this thing that we call the hot Big Bang. So I can start letting some air out. And we can watch that happen. I hope I don't let the universe go shooting off anywhere. I'm making some funny noises as it goes. Okay. So this is really just a kind of fun illustration, but I think it does put together all of those things that we've been talking about. The fact that the matter is evenly spread, that it's expanding, that it's really the space in between that's getting bigger. So this balloon would be an example of a positively curved universe, a universe like the bottom one here. But as it gets bigger and bigger and bigger, it looks more like the flat case because you lose information about the curvature. That's something else that we'll return to a little bit later as well. So let me just try and summarize these things before we start talking more about before the hot Big Bang. So I've told you how our universe is behaving. What I actually haven't told you yet is what's inside our universe, or much about it, apart from the galaxies, and I said there was dark matter as well. But because in general relativity there's an intimate connection between how things are expanding and what's inside the universe, we can actually measure what's inside the universe by watching its expansion, by watching what it was like at earlier and earlier times in these galaxy surveys or using the cosmic microwave background. And we get a very funny situation, by the way, which I feel I have to mention it because it's a talk on cosmology, but I'm not going to talk about it. I can come and give another talk about it another time. But we find that, most of our universe is not made up of normal matter that we call baryonic matter, which is you and me. That's the red thing here. Most is either made up of dark matter, which is about 25%, and then there's something else which we call dark energy. And when you use the word dark, that basically means we don't know what it is microphysically, but we can see its influence on the expansion of the universe. And dark matter, it particularly, is exquisitely well tested. Its gravitational properties in terms of galaxy surveys, and even within galaxies, dating back to Vera Rubin's time when she worked out rotation curves of galaxies. So it's not controversial that it's there. And actually, nowadays, it's not controversial that this thing, dark energy, is there either, even though we don't know what it is. And that's what's in our universe, and then this is how it's behaving with time. Just to summarize all the things I've said. We start off with everything very close together at early times. We have the formation of atoms. We have the cosmic microwave background that you see here. We have galaxy formation, first stars first, then galaxies, then clusters of galaxies, all the way through to today. And actually, this image isn't particularly realistic because it doesn't really show this expansion that I've tried to tell you about. And so I want to try and rephrase this picture a little bit to show that expansion a bit more clearly before I go on to the very early universe. And so let me go back to this picture, which is my sort of cartoon of the universe. Let me take a little section of it, and I'll blow this little section up. And I'm going to label the length of this section L, okay? And because the relative position of things is staying the same on average, what I can do is always look at a picture of this size, but as I go back in time in the universe, just rescale my axis. So instead of a length L, this same collection of matter would have been compacted into a smaller size, but I keep the picture the same length, the same size on the screen. So this is the technical word for this is co-moving coordinates, but basically what we're trying to illustrate is that the same stuff stays in the same patch of the universe, but the patch of the universe gets smaller as it gets more compact. And so this is today, and just to be a little bit more accurate, I'm going to do this in terms of the results of a simulation. So this is a simulation of dark matter in the universe, and actually galaxies will have formed at the sort of cusps of this, the hotspots in this picture. And because this is a simulation, they've literally run it from when the universe was very young through to today. So we can watch how this changes as this size of the box shrinks to half the size it was before, or a side of the box shrinks to half. So now everything is actually closer together, but you can see the picture looks roughly the same. It's changed a little bit. It's a little bit less, the structure's a little bit less well defined, but it's essentially the relative position of all the things has changed. So if I go back to today, let's do that one more time. Look at the sort of things in this picture, And then at earlier time, the same things are still there, they just look a bit different. And a little bit earlier times, they're a little bit more wispy, so structure hasn't quite formed yet. This is when the universe was a billion years old. And at even earlier times, it looks a little bit wispier again. And then again, this is just a cartoon really now, but at even earlier times, of course, it didn't look like this at all. It looked like the cosmic microwave background. So this is when the universe was 400 billion years old. And I think this is quite a powerful way of thinking about it, because we're looking at the same stuff, which has expanded out, but because we're looking at a finite picture, we can just imagine that the picture has been expanded every time. So if we go from early universe to later in time, to later in time, the universe is getting bigger, but all that stuff is maintained roughly its relative position. And now we're going back in time again. So the cosmic microwave background, even earlier times, atom formed, and then hotter still. So at very early times, we think the universe was even hotter. And before that is what I want to now talk a bit more about, which is what happened before the hot Big Bang, this thing, cosmic inflation, or alternatives to it. Now, just really quickly before I do that, I have one final demonstration to try and help you understand these kinds of images that we were seeing, and also the properties of the Big Bang itself. So yeah, hi, Dan, thank you. So sometimes we talk about the expansion of the universe as like an explosion away from a central point. The universe starts hot and dense and then explodes away. And if that were the case, this is roughly what it would look like. Oh, sorry. So an explosion that you're used to looks like a point of light, and then that point of light grows out to encompass everything around it. So as the light goes up, it's illuminating more and more of the theater as it goes, like an explosion bursting out, until it's illuminated basically everyone. But that's actually not at all what the hot Big Bang was like. The hot Big Bang was much more like this image I just showed you of some arrangement of matter that gets more dilute with time, and every point in the image is equivalent to every other. Every point in the image was the center of the explosion, so every point is equivalent to every other. And to illustrate that, maybe we can now put the house lights on full. So now you've got to imagine that every one of you is the center of the hot Big Bang explosion. Okay, so intense radiation everywhere, and you're all extremely close together, but it's in this image where, I've used these co-moving coordinates. And now, as the universe cools, the lights are going down, it's getting less dense everywhere. So all of you are the center of this explosion, and you're all experiencing the same thing, the same slow decay, it wasn't slow, but the same decay of the radiation, the brightness around you. And again, this makes sense if the universe went on forever in this direction, forever in this direction, up and down. You're all getting squished in together or expanding away from one another. But none of you is the center of that explosion. The center of the explosion is everywhere. And again, that's central to this idea that the universe is smooth and homogeneous and the same, equivalent in every place. All of us took part in the Big Bang explosion. And if we lived in a distant part of the in the distant part of the universe, we would have seen on average the same thing, the same kind of expansion away from this hot, dense state. Now let's talk about what's wrong with this model. So the first thing is this thing called the flatness problem. I told you that the universe we live in is extremely flat. The three dimensions of space look very like Euclidean geometry. The angles of a triangle add up to 180 degrees, just like they should, and everything else. But it didn't have to be this way. The universe could have been curved. I've argued that in general relativity, there were three different states that the universe could be like. Positively curved, negatively curved, or flat. And it turns out, actually, that flatness is a bit of a problem. The universe that we see being flat is a bit of a problem. It turns out that it's an unstable state. So as the universe grows, it kind of wants to get less flat with time. It wants to get more curved, or at least the curvature in proportion to the matter that's in the universe wants to get bigger. So we should see something that sort of on large scales looks more and more curved as the universe grows. But it still looks extremely flat to us. It's a bit like, balancing a pencil at the end of my finger here. It could be that way. It could just be balanced. But it's an unstable equilibrium. The pencil wants to fall over. And if you came into this room for the lecture and you saw a pencil standing up on its end and someone had put it there, you might want to know how it got like that. How did it get up on its end? Why had it not fallen over already? And that's sort of the state we find ourselves in with the universe around us today. There's no good reason why it's flat. We need some dynamical mechanism to make it flat. And then there's another problem which is actually much, much worse than the flatness problem, which is called the horizon problem, which is that when we look at the universe, as I've been telling you, it looks the same in every direction, and every region is equivalent to every other. But if I look over here, I look far enough away, I see the cosmic microwave background, that region of space that I'm seeing has not had any time to talk, to send a signal, because light propagates at a finite speed, from there to a region over here. And that's what you're seeing on this image at the moment. So back at the time of the cosmic microwave background, the circle that you see on the cosmic microwave background there is the region that light has had time to propagate in since the start of the universe, or at least in this hot Big Bang model since the start of the universe. And that white region there has not had time to talk to the other circle region on the other side of the sky. They haven't had time to talk to each other, to send signals. So why do they look the same? What caused them to be in equilibrium, in thermal equilibrium with one another, to have the same temperature, to have the same properties? Another way of seeing the same thing, the horizon problem again, is in this image where we're again using this kind of co-moving coordinate system. So we have a patch of the universe at the time of the hot Big Bang, and only some region of that is visible to the cosmic microwave background at later times. And then we see all of the cosmic microwave background today, at the universe today, and it all looks the same, but the patches that look the same to us couldn't have talked to each other before the hot Big Bang started. They couldn't have been in causal contact with one another. As these patches grow, light propagates from distant regions in, but it hasn't had time today to propagate, or at the time of the cosmic microwave background, these regions didn't have time to talk to one another, to send signals, to become the same. We call this the horizon problem. And then there's another problem I've got a little illustration of here, so don't take this too realistically, but it's called the homogeneity problem sometimes. Or just, again, the fact, why is the universe so homogeneous, so smooth everywhere? So imagine there was a patch of the universe at early times that was smooth, that had these nice properties that we want all of the universe to have, to be the same everywhere. And then there's some region outside it, this red region, that was different. So maybe it was really undulating, really different, and didn't look at all like our universe. Well, this inhomogeneity, this different behavior, starts to be visible to our universe over time. It starts to propagate into our region. So if the universe wasn't expanding, this is what this would look like. It would come in at the speed of light. Inhomogeneities would grow and kind of swallow up our nice flat patch, our nice smooth flat patch of the universe, like this, until it was all inhomogeneous. This is for a universe that's not expanding. Now imagine the universe is expanding, but in a way that is allowed by the hot Big Bang. So if the universe is filled with radiation that we know and love, or dark matter or whatever, then it would look like this. We'd have our inhomogeneous region in red, our region that doesn't look like what we want the universe to look like, and our nice smooth region in blue, which we'd like to be the whole universe. And it comes in, and it takes a bit longer now, but it still swallows us all up. And you see that on the axis I've labeled the universe during that time is growing. So again, this is this co-moving volume, this co-moving coordinate system. So this universe has grown in this time. You can see it's 1L, 2L, 3L. So it's taken a little bit longer for the bad stuff to get at us, but it has swallowed up this nice smooth patch eventually. And so why is the universe so smooth and homogeneous? Because over time it wants to get less so. Why is it so smooth everywhere on the larger scales? Why does it have that property? And this is where cosmic inflation comes in. Cosmic inflation is essentially designed or discovered, however you like to look at those things, to rescue this situation. And as I said before, it dates back about 45 years to the time of a physicist called Alan Guth. And he wrote in his notebook, I really want to have a notebook like this one day. He wrote in his notebook, spectacular realization. So, yeah, he's very famous now because of this spectacular realization, or at least famous within cosmology. Don't know if that's real fame or not. So essentially, he had discovered this behavior, or that this behavior, this inflationary behavior that I'm going to describe to you, could happen in the early universe. And actually, the models he was looking at the time don't turn out to be quite the ones that we think work today, or they're not really quite the models that we're looking at in modern inflation, but they're pretty close, and it's a pretty good idea. There was a bunch of other people working on this as well, just a little bit later, and even a little bit before Alan Guth, that sort of refined these models into what we think of as inflation today. But the basic idea is this. So we have the hot Big Bang, where the universe is growing, but if we wind the clock back, it's going to hit this singular point in a finite time. And we know that we have all these problems with it. Why was it so smooth? Why was it so flat? Why is it so big? And so we want to change the dynamics at early times so it behaved differently to save us from these problems of the hot Big Bang. And it turns out you can do that by adding something to the universe called a cosmological constant. So this was something that Einstein actually came across and put in his equations. And what a cosmological constant does is it tries to make the universe grow exponentially. So I'll describe what I mean by that in a second. Grow very large, very quickly. And it does that because as the universe grows, a cosmological constant actually, unlike normal matter, doesn't dilute. It stays the same density as the universe grows. So it sounds a little bit counterintuitive, but it happens. It can happen in nature that this exists, or within general relativity that this behavior happens. And so let me just sort of, so in this image that you're seeing this exponential growth before the hot Big Bang. Now I really want to illustrate what I mean by exponential growth, because it's a little bit of a sort of, sometimes people say inflation happened, the universe grew very quickly, but what do we mean by very quickly? We mean exponentially, or close to exponentially. And let me illustrate this. So an exponential growth is when you take something and you multiply it by a number greater than 1, and then you take the thing you had and you multiply it by a number greater than 1 again. And in this way, things accelerate in their growth. So I was asking some people today at work what a good example of that might be, something that's exponentially growing. They suggested student debt, which maybe isn't the best example. So instead of that example for you, not to sort of get universities into disrepute, I have an example from my son's Lego kit, or not Lego, but block kit. So exponential expansion or exponential growth is like this. So I start with something of one of them. Then the next thing in the journey is 2. So I've multiplied it by a factor of 2. It doesn't have to be a factor of 2, but I've multiplied it by a factor of 2. Then the next one is a factor of 4. A factor of 2 again. So there's 4 of them. The next one is a factor of 2 again. So there's 8 of them. The next one is a factor of 2 again. This is probably going to fall over. So there's 16 of them. Thank you. And I'm not going to try and stack these together, but this is 16 here, which is definitely going to fall over. Oh, no. And another 16. Yeah, okay. Another 16 there. And if I stack them together, it would be 32. So you can see it's gone from 1 to 2 to 4 to 8 to 16 to 32. And actually, there's only, 1, 2, 3, 4, 5, 6 of these. If I had about 15 of them, the thing that I'm growing would be about the size of the Empire State Building. So, by over here, when I had 15, it would be up in the sky. So this is exponential growth. This is growth at an accelerated rate with time. And that's how we think the universe was expanding. And what this does really is buy us more time. So where you thought you were going to hit a singularity, you can see that this curve, because it's an exponential growth curve now, can go on. Basically, it can go on forever. It can keep going into the past. And there's more time in the universe because of this exponential growth caused by inflation than we thought there was. And this is how we solve these problems, or how we think inflation solved these problems of the hot Big Bang that I've been trying to describe to you. So let's look at what happens, for example, in this growth of inhomogeneity problem. So we have our nice patch of the universe that we want, this blue patch. We have some horrible stuff outside, this red patch. And again, the universe, primordial universe, could have been very inhomogeneous, but we concentrate on a little patch that's nice and smooth. And when you zoom in on anything, basically it becomes smooth eventually. So that's this little blue patch. And now look what happens when I turn on inflation. So the signal from this horrible region is trying to get into the blue region. The universe is growing, though. Can you see the numbers getting really big? And it's growing really quickly, right? So it started at L, and now it's 1,000, 3,000, 4,000, 10,000, 15,000. It stopped. And this behavior, I'll run it one more time, is actually keeping light, the signal, keeping the signal of inhomogeneity, or the light signal, out of this nice smooth patch in the middle. Basically, 2 points start to move away from one another faster than the speed of light. So it's not violating relativity, because this isn't sending a signal faster than light, but 2 points that started here start to move away from one another so quickly that light can't come from one to the other anymore. The space in between is growing faster, such that the distance between the points is being stretched at a rate faster than the speed of light. And that stops this horrible inhomogeneity getting into a nice bit of the universe that we want to keep. And not only that, but you can see that this nice bit of the universe, this blue bit, which was smooth to start with, has got huge. It started out very small, but it's grown to be really big. And that's what inflation does for you. It takes a small patch of the universe that has the properties you want and blows it up into a really big patch of the universe really quickly. So let's zoom in on this nice patch that we have, because inflation does something else. It's not just that this patch is getting bigger and bigger with time, but even within this patch, there are other patches that are also getting bigger and bigger with time. And on some scale, which I won't go into, but it's called the horizon scale, these patches can't communicate with one another anymore. They're moving away from the other patch faster again than the speed of light, so faster than signals can come from one patch to the other. So we turn this patch of the universe into lots of disconnected patches that are acausally disconnected. So it started as the same patch that was causal, but it becomes lots of patches that are acausal, that can't communicate with one another. And this process goes on and on. I don't have any more images, but it goes on and on and on until you turn one patch, which is roughly what we call the horizon size, into many, many patches that are roughly the horizon size. Because remember, this patch that I'm showing you on the screen is growing all the time. The horizon size stays roughly the same size, but the patch is getting huge. It's getting bigger and bigger and bigger. It's inflating. And that solves this homogeneity problem, because it makes a very small patch very big. And I think you can already see it's going to solve the horizon problem for us, because the horizon problem was that we had many patches that couldn't communicate with one another, looked like they weren't communicating with one another. But in inflation, we have lots of patches that can't communicate with one another, but they all started at the start as the same patch. So they were all in contact with one another to start with, and then grew. As the universe grew, they became disconnected, they became acausal. So it should be that they all have the same properties. Let's think about the flatness problem first. The flatness problem is simply that if you take this patch, if you zoom in on anything, it looks smooth when you get to small enough scales. So this could be down to even the Planck scale. And then you blow it up. So here, we've got a picture of a sphere that's just been blown up bigger and bigger and bigger. And as the sphere gets really, really large, it starts to look flat. And if it does that really, really quickly, these inhomogeneities can't ruin the nice smooth picture that you get. So inflation solves this thing, the flatness problem. And I already mentioned that it solves the horizon problem. There's different ways of looking at it. One is this sort of breaking up into lots of disconnected patches, which is what we want. It's what we see in the early universe. Another way is that there was simply more time, because I showed you that the universe didn't have to start at this singular point anymore. It could have gone on into the past for a very long time. And that solves this thing we call the horizon problem. Now, I said inflation could be driven by this thing, the cosmological constant. But that's not really a good model, because the cosmological constant stays constant, it stays the same, and inflation would never end. We'd never get back this hot big bang that we know and love. So instead, we actually think that inflation is driven by a field called a scalar field. So a scalar field is just a fundamental field of nature. The only example that we know actually exists is the Higgs field, but we do actually have an example of a scalar field in nature. And a scalar field just takes a value at every point. So it's a bit like the light we were looking at earlier. Every point in the universe, the scalar field takes some value. And in a homogeneous universe, a universe that's the same everywhere, the value of that field is the same everywhere. And the dynamics of the field are that it has some potential energy associated with it, some energy everywhere associated with the field being there. And it wants to minimize that energy. And it looks a bit like this. It starts with some energy, and it's a bit like a ball rolling down a hill. And it minimizes its energy with time until it reaches a minimum. And as it does that, in the early stages of that behavior, this energy is changing very slowly. It's called slow roll, in fact. Because it's changing so slowly, it looks a bit like effective cosmological constant, because it's changing with time, very little as the universe is expanding. But it does eventually reach the minimum of the potential, and it stops behaving like it was before, and inflation ends. So it's driven by this fundamental field called the scalar field. Now, we don't know what that field is, and so this is one criticism that can be leveled at inflation, but it is a fundamental field. Let's add quantum mechanics to that picture. So in quantum mechanics, things aren't just there or not there, but they can pop in and out of existence. And as long as they do that over a short enough timescale, they conserve energy and everything's fine. So what that means in this picture of the field is that the field doesn't really roll down the potential in a completely sort of classical and uniform way. Remember, we're dealing with very high energies here. The energy scale is very high, and so quantum mechanics should be playing a role. But there's a bit of fuzziness to the field's position, which I'm trying to illustrate here. And that means in one part of the universe, the field might have a slightly different value to another part of the universe. But it still rolls down, and eventually this fuzziness sort of stops, and it ends up in the minimum. And the consequence of that fuzziness is actually the origin of all structure in the universe. Because I told you that inflation makes things very smooth, very similar everywhere. But of course, that's not actually good enough for our universe, because although on the larger scales our universe looks very similar everywhere, we know there must be structure in it. We know there must be regions of the universe that are hotter and denser than other regions. Otherwise, there wouldn't be galaxies that form over time at all. Even though they start from very small over and under densities, they grow over time. And what happens with inflation is that these quantum mechanical fluctuations in the field can actually produce this structure. And they do it in a very beautiful way. As the universe grows, a particular wavelength gets stretched with it. And when it gets to a certain size, it behaves. What started as quantum mechanical behavior becomes classical behavior and freezes in the universe, becomes an over or under density. And in this little sort of simulation, I show you what happens. So we start with a universe that is kind of flat, kind of the same everywhere. Not quite. A little bit of structure, but only a little bit. So it's going to allow inflation to start. And then these quantum mechanical fluctuations are going to start being expanded to large scales, to classical scales. And so what started smooth as these fluctuations grow and are stretched to large scales becomes bumpy, and becomes bumpy on shorter and shorter scales as the universe becomes larger and larger. And so this is a natural consequence of what's going on during inflation, that these fluctuations grow, and what started as a flat, smooth universe gets these classical undulations in it. And when we look at the spectrum of these undulations, so what they look like, if we zoom in on them, we can compare that with things like the cosmic microwave background, or this is now a 3D picture of that slice, again from a simulation. We can compare that with what the sort of dark matter field looked like at early times. This is the picture I showed you earlier from this Millennium simulation of dark matter. And we see that they agree. Okay, this was just a cartoon, really, but we see that they agree to really exquisite detail. Because there are different ways that these fluctuations could appear. One is called scale invariant, which basically means that on any scale, the fluctuations look the same. But they could also have been differently. This is an extreme version, and the next slide is an extreme version of how they would look different. So I'm going to speed up slightly to get to the end, but this is an extreme version. But when we compare on a very sophisticated statistical level what the fluctuations that I've just shown you been created look like in comparison to those of something like the cosmic microwave background, they agree to an exquisite level of detail. And that's why we believe inflation as a good theory. So just to give you a summary, inflation takes an inhomogeneous universe, zooms in on a little bit, blows it up, adds some quantum mechanics, and gives you a structured universe at the end that agrees with our observations. Now, if I could just have a couple more minutes, let me tell you what some of the problems are with inflation. What is the inflaton field? We don't know. So there are lots of ideas floating around. One thing is that it could be a field that enters physics at very high energy scales, such as in string theory. So in string theory, we actually live in a higher dimensional universe. Those dimensions get wound up, and when they get wound up, they essentially give you a field to play with. So a field determines the size of the extra dimensions, for example. So there's lots of scalar fields floating around in string theory. Or it could be something more prosaic. So extensions of standard model physics have extra scalar fields in them as well. But the truth is we don't know. And this is taken from a paper called Encyclopedia Inflarastis. And here are just some of the models that are in that paper. So each of these is a different model of inflation. Okay, I'm going to speed up a little bit. Yeah, okay, I could go on. Okay, these are just a few of them. So a critic might say, well, there's too much freedom. Okay, there's too much freedom there. We don't know what the field is, and actually, you've got so many options, you can more or less engineer it to do what you want. So have you really explained anything in the first place? And it's a fair criticism. I don't agree with it, by the way, but it's a fair criticism. Then there's another little problem, which is what happens when inflation gets too good? So by that I mean we have these fluctuations, these quantum fluctuations that produce structure, but sometimes these quantum fluctuations can get very big. In particular models of inflation, they can get very big. And in these separated bits of the universe, these disconnected bits of the universe, start behaving extremely differently from one another. They start behaving like separate universes, like different universes entirely, where the physics is entirely different to the universe that we live in. And some people think this is a good thing, and some people don't. Some people think it's a good thing because it sort of explores all the possibilities of physics, and then we live in a nice bit of the universe when inflation ends. But it essentially creates these kind of disconnect. This is just sort of an illustration of it from someone else's talk, but at the Perimeter Institute, they create these bubble universes that are disconnected with one another. And so inflation today is this sort of evolving field where we can compare with observations with exquisite levels of detail. We know it's broadly speaking a good theory, but there are some of these drawbacks that people don't like. And also it's fair to say that it doesn't really explain, for example, singularities in general relativity, although it pushes that problem way back in time, it doesn't really solve it. So some people like alternative ideas, and I've just 2 minutes, let me just share a couple. One is this, that it could be a big bounce. So it turns out you can get dynamics in a bounce that are very similar in some ways to dynamics in an exponential expansion. So just like in an exponential expansion, different regions of the universe are becoming disconnected with one another. The same thing can happen when the universe collapses, when it goes towards the singularity if certain behaviors are met. So in this kind of bouncing model, which then bounces into a growth period, we also have this behavior of the universe disconnected, bits of it getting disconnected from one another, solving the horizon, solving the flatness problem, and so on. And that kind of model, which is sort of argued by some people, really takes the singularity problem head on, because it really requires us to go through a bounce, to go through a contracting phase into an expanding phase. Now, the truth is we don't really know how that could happen, but there are ideas floating around about how those kind of bounces might have worked, which are, I would say, not well fleshed out yet, but are interesting ideas. And of course, that leads on to the idea that the universe could have gone through cycles, potentially infinite cycles of this kind of behavior. Or it could have gone through cycles that grow with time. And actually, this is a really early idea, going back to Tolman, of cycles that grow. And because every iteration of the universe is a little bit bigger than the last, is solving things like the horizon and the flatness problem that way, though it doesn't really give an origin for structure in this picture. But it's another really nice idea that's not quite fully fleshed out in the way that inflation is, and isn't as well developed or as well compared with observations, but is a nice thing, which you can ask me about at the end if you want. So this is my final slide. Let me just say then what we've arrived at. So we've arrived at a picture of a hot Big Bang universe, but before the hot Big Bang, there was inflation. Inflation made the universe very large, very smooth, very even everywhere. At the same time as doing that, it put these little quantum fluctuations that got expanded to large quantum fluctuations, expanded to very large scale over and under densities in the universe that were origin of all structure. So inflation provides the universe that we see around us, including the over and under densities that are going to form the hotspots in the cosmic microwave background, the first stars, the galaxies around us, and then, of course, right at the end, us as well. So sometimes you hear that we all come from stardust or something like that. In this inflationary universe, we all come from quantum fluctuations. And that's me.